Thank you for having me. I'd like to thank the organizers for accepting my talk, even though I'll be very honest right now, it's not, there's no explicit ties to reverse mathematics. It's a computable structure theory talk, but if you think there might be some connections and you'd like to talk to me after, I'd also love to chat with you. So yeah, thank you for accepting my talk anyways, even if it's not about reverse mathematics. So I'm going to be talking about content mostly from two papers. These two papers are available on my website. I put the archive links up there. One of them, the first one was just recently accepted into a journal, so I thought it would be a good time to just sort of mention it. But I also, I did not plan for a sequel paper, but there's also a sequel paper out now. The preprints are both available on my website if you'd like to take a look at them after the talk. So that's what I'm going to be covering today. So this is the outline. I'm going to just provide some background sort of for the story I want to tell about this project from my dissertation. And then a lot of the work started in the CE degrees. So some natural directions, let's just go outside of the CE degrees. And then I also went outside of the class of directed graphs. And then if there's time, I just want to sort of give a very rough sketch of the proof of the one generic result, which I'll state at some point in this talk. Okay, so let's just start with some background. So in computable structure theory, so we had some nice lectures last week. The notion of computably categorical was mentioned last week. So for this talk, I'm going to just assume every structure I'm talking about is computable. So I say that a computable structure A is computably categorical. If for every computable copy B of A, you can find a computable isomorphism between A and B. So here's an example that you can sort of hang on to throughout the talk. So Q, the rationals as a linear order is computably categorical. Why is that true? Well, you just sort of do the very sort of simple back and forth argument, and then you can build the computable isomorphisms that way. But on the other side, you have the natural as a linear order is not computably categorical. So why is that true very fast? Well, you can sort of think about building a copy of the natural numbers, but you sort of just diagonalize against any computable function and prevent it from being a computable isomorphism. So of course, there's a lot of different examples of things that are computably categorical and things that are not computably categorical, but those are just the examples I want to just give you for now. Okay, so we look at this notion, and there's a few ways to relativize this. So the very first way it was relativized, and sort of the one that's really well understood, there's a lot of things on this about this in the literature, is the following relativization. So you say a computable structure A is relatively computably categorical if for every copy B of A, and here we're not asking the copies anymore to be computable, they cannot be computable. If for every copy B of A, there is an isomorphism between A and B, and you can use B to build that isomorphism. You can use data from B to build that isomorphism. So this is very well understood. There's a lot of stuff on this in the literature already. In fact, last week, it was mentioned that there's a very nice syntactic characterization of this relativization in terms of what was called Scott families. Okay, so the relativization that I want to focus on for this talk is not exactly, it's not this one, but is related. So here, what I'm going to do is I'm going to fix the Turing degree D, and I'm going to say A is computably categorical relative to D, and then that's a mouthful, so I'm going to say CC relative to D moving forward. A is CC relative to D if for every D computable copy B of A, there's a D computable isomorphism between A and B. So you're going to make a hard commitment on how complicated your copies are, and that commitment, you're supposed to also match the complexity of the isomorphism to that commitment. Okay, so that's the relativization that I want to focus on today. So this is relatively new, and there's things about this. So an observation I want to point out is how is this newer relativization related to the older relativization? Well, if you have something that's relatively CC, then you can think of it's equivalent to being CC relative to all of the degrees at the same time. So, and then you can sort of see that from the definition up here is, here we're not making any commitments, so if something is relatively CC, then it should be CC relative to all degrees D at the same time. So that's sort of an important concept that I want to emphasize here, because we're going to start looking at things that might not be CC relative to all degrees, maybe to some of them, but not all of them, in sort of weird ways. For the second one? Yes, it's an equivalence. Yeah, it's an equivalence. Yes. Yeah. You can also just think of it that way. Yeah. Okay. So sort of a new way of thinking about this that I wasn't thinking about this in this way before. So given a computable structure A, you can form the set of degrees D sub A here. So you can think about the set of degrees such that A is CC relative to D. So if we assume enough determinacy, then the set of degrees either contains a cone in the Turing degrees or is disjoint from one. Okay. So in this way, I kind of want to start looking at being CC relative to degrees as sort of like on this like cone kind of thing. Is like either maybe so I'll just continue so that I can better describe what I mean by this sort of imagery. Okay, so since we want to speak about cones, I want to introduce this sort of auxiliary definition in this paper by Barbara Chima and Matthew Harrison Trainer in 2017. They defined that a structure A is computably categorical on a cone above some degree D if for all C above D, whenever B and C are C computable copies of A, there's a C computable isomorphism between B and C. Okay. So, and then how is that related? Well, going back to like the very older relativization, if your structure is relatively computably categorical, then you can think of it as being computably categorical on a cone above zero. So it already sort of decides, okay, I'm going to just be CC relative to all the degrees on a cone based at zero. And of course, A is CC on a cone above a degree D if and only if it's computably categorical relative to every degree above D. Okay, so that's how those are connected. And the reason why I want to sort of put this image of cones in your mind, where some of the cones are already based at zero, is due to this following fact. So this follows from some results by Ash, Knight, Manasse, and Slayman, and also a Gonchar result. So if A is a computable structure and it's computably categorical relative to some degree D above zero double prime, then A has what we call a zero double prime computable sigma 1 Scott family. So remember, that's the nice syntactic characterization. And that's actually enough to get you that A is CC relative to every degree above zero double jump. Okay, so sort of the image that I draw a lot is you have the computable degree, you have zero prime, and then you have zero double prime. So for some structures already, you can sort of have them be CC relative to all degrees in this cone above zero. Now, there might be some that are not CC relative on that entire cone above zero, but maybe with that fact above there, maybe the cone actually moves up to being based at zero double prime instead. Okay, so I'll go back to this where some of the cones here are going to be based at zero, but for now, I'm going to say at least for any computable structure, the cones up here are going to at least be based at zero double prime. And what this means is you can have computable structures where it's CC relative on this entire cone above zero double prime, or it's not CC relative to any degrees above zero double prime. So you can sort of fill in this cone to indicate that it's CC relative to any of them, or leave it blank to say that it's not CC relative to any degree above zero double prime. Okay, so going back to that set of degrees that I defined on the previous slide, that set either contains the cone above zero double prime or doesn't contain any cone at all. Okay, so if it has to contain a cone, it has to at least contain the cone above zero double prime. Okay, so there's a big gap here, right? At least, right? So for all computable structures, it stabilizes on this cone above zero double prime. Well, what happens before zero double prime? So that's sort of one of the main topics I want to go over today. So let's just focus on the gap below zero prime. So above 0 and below 0 prime. So already below 0 prime, this notion of relativized categoricity does not behave well at all. So this is a result by Downey, Harrison, Trainer, and Melikov. They showed that there is a computable structure A, and increasing linear order of CE degrees starting with 0, such that A is computably categorical relative to D sub I for each I. A is not computably categorical relative to E sub I for each I. And just by sort of a artifact of their construction, A is computably categorical relative to 0 prime. So they've already witnessed that, there's a structure out there, it's really weird, and there's an increasing sequence of CE degrees where it can change its mind every other CE degree. So it's not monotonic at all, already below 0 prime. Okay. So, yeah.
Are they uniform?
Yeah. So the way they built it, uniform in the.
Like is there,
So it's been a while since I've looked at this, but I think the way they did this is they built the first CE set and then they did joins to build up the spine. Yeah. So that's how they did it. Yeah. So I made this worse. It's not just an increasing linear order of CE degrees that can sort of witness this behavior. It can be any partial orders. It can be partial orders of CE degrees as well. So here I say let P be some computable poset and let P be computably partitioned into P0, P1. Then there exists a computable directed graph G and embedding H of P into the CE degrees where G is computably categorical, G is computably categorical relative to every degree in H of P0. So in the images of the points here, and G is not computably categorical relative to any degree in H of P0. Okay. So it doesn't have to just be an increase in linear orders, it can be a poset of CE degrees. You can also take the version where you start with something that's not computably categorical. It doesn't change the proof that much. So you could either have the graph G start as computably categorical, or you can have it just already not be computably categorical there. So some things to point out here is one particular thing that I sort of, thought about is it's not just this result, but the other result that I also mentioned, both examples of the structures that witnesses these facts were both directed graphs. So very early on, some people asked me, well, could you do it with things that were not graphs? And then, of course, this is all being done in the CE degrees. So, what is the story for things that are not CE? Does the story sort of change? So that's sort of the next part of my talk. So I'm going to sort of focus on just looking at things that are not CE degrees. What is the behavior of categoricity relative to a degree to things that are not CE? So first I want to just start with this definition. We say a set A is n-generic if for all sigma n set of strings S, there exists an M such that either A up to M is an S, or for all extensions of A up to M, tau extensions, tau avoids S. And we say a degree D is n-generic if it contains an n-generic set. So usually, if you want to look at things that are not CE, usually the first thing you might want to consider are generic sets. So is the story different for generic sets? So a degree D is low for isomorphism if for every pair of computable structures A and B are decomputably isomorphic if and only if they were already computably isomorphic. So this low for isomorphism is sort of a weakness notion. If D is low for isomorphism, you can think of that as being very weak. It doesn't give you anything new about the isomorphism type between these computable structures. Okay. So how is that related to what I've been talking about? So first, I want to give this result by Joanna Franklin and Reed Solomon. So they showed in this paper that every 2 generic degree is low for isomorphism. So so what that means is every 2 generic degree doesn't tell you anything new about the isomorphism class of computable structures. So what does that mean for the story? Well, this is sort of the first instance of where the things that I could do in that construction for that post-it result actually just doesn't work at all. So in the sense that there's no hope of building a computable structure A where it starts being not computably categorical, but changes its mind to being CC relative to some 2 generic D. So this is already a first instance of sort of an obstruction of where the techniques just don't apply at all. So, and this is sort of really coming from the property of D being a 2 generic. It just doesn't tell you anything new about the isomorphism class. So there's, in a way, it kind of just prevents this structures from changing their minds from being CC to being CC relative to a 2 generic. Okay. So I guess I spoiled it. So one might wonder, okay, for 2 generics, you can't make a weird structure like I did with the post-it result, but can you do it for a 1 generic? And it turns out you can. And that's sort of, I'll sketch out the proof of that if we have time later on. So there exists a properly 1 generic G such that you can have a graph change its mind from being not computably categorical, but it's computably categorical relative to that 1 generic. Now, of course, there's a bit of a gap there. I don't know what the case is for weekly 1 generics. I haven't looked at that yet. So if you ask me about that, I'll probably just tell you I don't know at this moment. Yeah, okay. So that's at least the case for generic degrees, which are not CE, is for 2 generics, you can't build a structure that changes its mind, but at least for a 1 generic, you can still build structures that can change. So now I just want to now go to that thing I pointed out where the post-it result was for directed graphs. The witnesses were directed graphs. So what's the case for things that are not directed graphs, so outside of the class? So here I want to start with this question. So for structures other than directed graphs, can you produce an example that witnesses the pathological behavior in the post-it result? So for some classes of structures already, the answer is positive. So this is really a corollary of some very well-known results already. So for example, by the codings given in this Hirschfeld, Kusinov, Slinko, and Shore paper, you have these classes of structures that are complete in the sense where you can sort of code directed graphs with certain properties into an example of these structures, and they will retain the same computability theoretic properties as the structure you started with. So for example, for symmetric irreflexive graphs, partial orderings, lattices, rings with 0 divisors, integral domains of arbitrary characteristic, commutative semigroups, and 2-step nilpotent groups, you can certainly just take the graphs that I built, put the code, slap the coding on top of those graphs, and then produce examples of these classes of structures that have the weird behavior with the post-it result. And then by this paper that Russell Miller did with a bunch of people who I don't think were logicians, here they explored the notion of like sort of a computable functor. They also showed that the class of countable fields is sort of complete in sort of the same sense as in the HKSS paper. So in these classes of structures, you can have something that is behaving in such a pathological way in the post-it result. Okay, so for those, it's a positive answer. Now, what about for things where you can't have examples of structures that change their behavior in this chaotic way in the CE degrees already? So I want to focus in particular on linear orders. So for the class of linear orders, I want to start off by saying, so this was proven very, very long ago. Ramel showed that a computable linear order is computably categorical if and only if it has finally many adjacent pairs. And what I mean by an adjacent pair is that A and B and L are an adjacent pair if A is less than B and there's nothing in between A and B. So the first example I gave you, a computably categorical structure, was Q. And remember, that has no adjacent pairs. So it's computably categorical, whereas if you look at the natural numbers, it has infinitely many adjacent pairs. So it can't be computably categorical. So, and then in fact, this because of the nice syntactic characterization of relatively computably categorical, well, it does take some work, but you can see that every linear order that's computably categorical has to also be relatively computably categorical. Okay, so in some sense, if it's already CC relative to 0, then it's just forced to be CC relative to all of the degrees at the same time. So in some ways, the limiting behavior of CC relative to a degree stabilizes already at a cone based at 0. That's the story for computably categorical linear orders. Okay. Now you might wonder, okay, well, you have the version of the poset result where you start with something that's not computably categorical. Can you have a computably categorical linear can you have a linear order that's not computably categorical, but you can change its mind at some CE degree? Right? Does this cone not exist for linear orders that are not computably categorical? Would anyone like to guess? Oh, can you change its mind to some degree above 0? Oh, sorry. Sorry. So it turns out, I'm not sure why it took me so long to realize this. I'm sorry. No. So it turns out even if you start with something that's not computably categorical, for linear order, it actually forces it to not be computably categorical relative to any degree above 0. And this is actually not too bad to see if you just read Ramel's 1981 paper. You just look at the construction that he did in the backwards direction, and then it's easily relativized to any degree d at the same time. So what that means is for the class of linear orders is if you start with something that's computably categorical, it has this cone, it's CC relative to any degree on this cone, and if you have something that's not computably categorical, then already it's not CC relative to any degree at all. Okay. So you can't produce an example of a linear order that can change its behavior chaotically in the CE degrees. Okay. If you think about it for a bit, if you know anything about Boolean algebras, it actually turns out that the same thing holds for Boolean algebras. So what we have is for these classes of structures, you can have them sort of behave in this very poor way in the CE degrees, but for linear orders and Boolean algebras, there's sort of some sort of structural properties that they have them have this all or nothing behavior on either side. So just to summarize before I go over the sketch of the one generic result. So for some classes of structures and degrees, there exists some structure which I will call poorly behave in the sense that its categoricity behavior changes relative to sort of in the chaotic way in the CE degrees. So it can change its mind. And for other classes of structures, so linear orders, Boolean algebras, and degrees, two generics, there's some sort of obstructions to this method. So in the side of the structures, the structural results, properties of linear orders and properties of Boolean algebras prevent you from doing these priority arguments that that sort of encode that weird behavior where you can change its categorical behavior relative to some degrees. And then for two generics, there's some property of the two generic degrees that also sort of prevents you from doing that sort of game. So there's no structures who can change their categorical behavior relative to a degree. And of course, I think I said this out loud, in particular for computable linear orders, their limiting behavior for categoricy relative to a degree already stabilizes on a cone above 0. Okay, so we know from every computable structure, it stabilizes, their categoricy behavior stabilizes on a cone above 0 double, but at least for linear orders and Boolean algebras, it already stabilizes at the level of 0. Now, that's not every structure that every computable structure theorist cares about. So there's a lot of structures I haven't mentioned at all or haven't looked at all. So in particular, one such class of structures that I would be interested to know the answer to is maybe something like trees of finite height. I believe trees of finite height are, trees that have trees are computably categorical if and only if they have finite height. Maybe I'm misstating that. It's not clear to me how the proofs, I haven't really sat down and read through those proofs, but it might be the case that if you have a tree that's not computably categorical, maybe their categoricity behavior already sort of stabilizes at a code above 0. But so there's a lot of things to look in here, but I think most of the work is just going to be done by looking at the proofs very carefully and seeing if those proofs relativize or not. So for the remainder of the time, I sort of just want to sketch sort of the construction that you would need for some of the things that I stated. So some of the results that I stated here. So remember, this is the theorem. So there exists a properly one generic such that there's a computable directed graph A, where A is not computably categorical, but is computably categorical relative to G. So I sort of want to sketch out what it takes to build a graph in that fashion. But don't worry, I'm not going to talk too much about priority trees or infinite trees. I'm going to just draw a lot of pictures and then sort of wave my hands around a lot. Okay, so yeah, so I'm not going to make this a secret. It's a priority construction with infinite injury with these 3 types of requirements. So the first requirement is just your typical, I want to make a one generic G. So there exists some initial segment of G such that sigma meets the jth CE set or any extension of sigma avoids Wj. I'm not going to focus at all on what the strategies you will do for that one. It's just a typical strategy. The thing that's kind of newer is I have these categoricity requirements. So the first one says phi sub E between A and B is not an isomorphism. So we're building a graph A. And we're also going to build a computable copy B of A such that there's no computable isomorphism between A and B. And then lastly, we have these SI requirements. So if A looks like it's isomorphic, if A really is isomorphic to this ith G computable directed graph, then there exists a G computable isomorphism Fi between A and Mi. So if they really end up being isomorphic, you should really build that isomorphism at the end. Okay. So I'm going to focus primarily on what you do for PE and SI. And then I'll talk a little about sort of the things that happen when you do both of them at the same time with the one generic requirement and sort of the issues and how you can solve them. So we're going to build the computable directed graph A in stages. So at stage S0, you have an empty graph. And then at stage S greater than 0, you're going to add 2 new connected components in this way. So you're going to have a node, and you're going to label it A2S. And you're going to have another node, and you're going to label it A2S plus 1. Is that big enough? I can make it bigger if you want. Yeah. So what do you do to these nodes? Well, you're going to attach a 2 cycle to each one. And then for the node with A2S, you're going to attach a cycle of length 5s plus 1. So I'm going to just label this 5s plus 1. And then for this guy, you're going to attach a cycle of length 5s plus 2. And those are your connected components. You're going to add those components at every, this is a global action, you're going to do it at every stage s greater than 0. And of course, you add these cycles in such a way that you can sort of differentiate between the two of them. So I'm going to just refer to these connected components by the labels on their root nodes. So the root node A2S in our graph, so that includes the nodes and any other connected nodes with these cycles. I'm going to just refer that as to that as a 2S connected component of A moving forward. Okay, so this is sort of the base of your graphs. Now, what's going to happen is throughout the construction, you have to do different things depending on what things happen. So there's actually 3 configurations happen. So the first configuration is just where you do nothing at all to those connected components. So I'm going to just redraw that. So this is the first configuration. Is it turns out that for some reason, for any sort of reason, these two connected components never get messed with. They just, you add them and then you never have to add any loops to them. And you just never have to do anything to them. Now, another configuration of the connected components here is you start with configuration 1. But then at some point, you have to diagonalize against something. And so what do you do when you want to diagonalize against something is you're going to just add loops in very specific ways. So for example, maybe here you add a cycle of length 5s plus 3, and then you add a cycle of, color code this, you add a cycle of length 5s plus 4. And then because you want to make sure that B and A are isomorphic, you're going to have to also add additional cycles. So for this guy, it now has a cycle of 5s plus 2, and here it has a cycle of 5s plus 1. Okay. So that's another configuration that can happen, is you're going to add these red and blue loops to sort of homogenize the 5s plus 1 cycles and the 5s plus 2 cycles. Okay, now the third configuration is sort of an extension of configuration 2. I'm going to not label the nodes anymore. I'm going to sort of just rely on color coding, or at least the cycles. Plus 1. So here we have these nodes, these cycles. And then this comes up because, I'll mention this later, why this comes up. So the last configuration that you can have is these two connected components actually end up just looking like the same thing. So those are the three possible ways your connected components can end up being. Is they're separated by so first, either they're separated by the 5s plus 1, 5s plus 2 cycles, or they're different from each other because of the pink and blue loops, or they just look the same. So this is the main tools that we have for this construction. Okay, so let's just talk about the PE strategy. So remember, the PE strategy says, I don't want to make these computably isomorphic. So what you're going to do is let alpha be a P strategy, and let's say alpha is eligible to act at stage S. It's acting for the first time. What it's going to do is it's going to pick some parameter n alpha, and it's going to say, okay, the nodes connected to those parameters, I'm going to use them in my diagonalization. Okay. And then what it does is, okay, so here I'm going to sort of just expand on this graph here. So let's say this is the graph A, and then this is the graph B. So what I didn't mention is we're also building B up in the same way, but maybe we have to add loops or whatever. So here, right now, we have a copy of these A components in B. And then we're going to alpha is just checking, well, at any point, does it look like phi E gets the isomorphism right? So it's going to check if phi E maps these correctly. Okay. Now, if phi E never maps these two correctly, you're done. You win for free. But if you do see that phi E actually might get this isomorphism correctly, you want to make sure that it can't ever be correct. Okay, so if not, alpha takes action. Now, if alpha sees that these phi E's pop up, then you're going to go into configuration 2. Is you're going to say, okay, I'm going to put the red loops here, the red cycles here, and then the blue cycles here. And then just because you want to make sure that these graphs are isomorphic, you have to add these homogenizing loops. Okay. Now, and then you've successfully diagonalized on these two pairs of components. Okay, so that's just PE in isolation. It's a very simple strategy, but it can cause a lot of problems later on if you do it with other things. Yeah, so that's just the main PE strategy. Now the basic strategy for SI. So remember, SI says if you think that these graphs are isomorphic, you need to build the isomorphism at the end. So the general goal of that is you're going to go through each pair of connected components, and then you're going to just check, okay, for these pair of components in A, can I find copies of them in this directed graph that's G computable? Okay. Now, the thing that can happen is the following situation, especially when you're building something like one generic that can change its initial segments at several points in the construction. So what can happen is maybe, so what can happen is, so let's say you have A, and then you have some MIG. You have so let's say your SI strategy says, oh, well, for these two connected components, I found a copy of them in MIG. So what I'm going to do, I'm going to do the simplest thing one can do. I need to build the isomorphism at the end. So I'm going to just send this component to this component. And I'm going to call that my FIG. Be computable. Now what can happen is this has some GUs that you can have some control over during the construction. So I'm going to just call it U. Now what happens is maybe later on some R strategy actually says, oh, I think that G up to U or G up to U should look something like the following. And then what can happen is because G up to U changes, maybe that makes this map disappear. And maybe it even goes as far and says that these cycles disappear. So obstructions like that will happen. That's sort of the least annoying kind of obstruction that can happen. And if that happens, well, we have that alpha can just sort of check for any G changes up to some previously defined use, and then it'll determine what component it should sort of fall back on. Okay. For example, for the SI strategy that was working with this graph in particular, it'll sort of look for the least component where this kind of injury happened, and then it just has to go back and say, okay, well now I'm matching up these components, so I just need to wait until I find components that look like them in B. So, yeah. Now, so that's just sort of very roughly what the S&P requirements are. Okay? And as you can see, it could be the case that maybe some interactions here happen. So I'm going to just keep this picture up. Okay? So what could happen is the following. You have copies of these A components in B, and some S requirement says, okay, I'm going to define my FIG map with some U's, call it just U for now. And then what can happen later is, or what may have happened already, I guess, is maybe at some point new loops appear on this side. So maybe for some reason this was picked to be part of some diagonalization strategy. So that's also another interaction that can happen is while S builds these isomorphisms, those P requirements are adding loops and maybe messing up with the progress of S requirements. So that's sort of the first interaction I want to point out, is the PE requirement may have, it'll pick some components, and maybe it'll wait a really long time until it actually has to diagonalize. And while it's waiting, some S requirement catches up and says, oh, I have to match these components up. So they do it in this way. But then later the P requirement says, oh, actually, I want to diagonalize on these components. So I have to add these loops. So how do you solve that? So in the tree of strategies that we have, we just have sort of this like waiting outcome where if P wants to diagonalize with its connected components, then it just has to wait for any higher priority S requirements to catch up. And then the second interaction here that I want to point out, that's I've sort of pointed out maybe a little, is changes in initial segments of G can make computations that disappear, reappear again. So in particular, that's sort of why this configuration is really important. It could be the case that maybe you diagonalize in this way because you thought an initial segment of G is supposed to look like, it's supposed to show that, so maybe you saw this initial segment of G and you said, okay, A and B should look like this. But then later, some isomorphism that some S requirement was building comes back. And then now you could be wrong about how those loops are supposed to be positioned. And so sort of in the very simplest way you can do it, you can just super homogenize these components. And then maybe you can super homogenize the components. And then it turns out that actually doesn't undo whatever that P requirement does. Using some sort of very formal argument, it's just because it turns out that a P requirement in that way wasn't even on the true path at all. So, but this is something that wasn't at all a part of the post-set result. This comes up sort of just because you're working with the one generic instead of CE sets. Okay. So those are the two main interactions that happens in the priority construction, and then as long as you can solve those, you can just build the graph and the one generic G. So that's pretty much it. So sorry it's a shorter talk, but thanks for your attention, and I'd be happy to answer any questions.